I'm going to be explaining how to find the time-dependent material and energy balances for a CSTR. So a CSTR is a continuously stirred tank reactor. And we're going to be trying to find the time-dependent concentration of A and the temperature as our cooling water in the jacket around our tank changes. So we know that we have a tank that has a mixer inside of it. So the mixer makes this tank perfectly stirred, which means that the concentration of A and the temperature inside of the tank are going to be the same as the flow going out, or the concentration of A and the temperature in the flow going out. So we know that we have some flow going in. We're going to call this Q. We also know that inside of this flow, we have an initial concentration of A. We're going to call that CAI. And this flow has an initial temperature, which we're going to call TI. So we also know that this tank is an overflow reactor, which just means that the flow going out comes out at the same height as the liquid that's inside of the tank. And this means that our volume does not change inside of this tank. So the volume stays constant. We also know that inside this reactor, we have A going to B. So that's a first order reaction, so we know that 1 mole of A reacts into 1 mole of B. And like I said in our problem statement, this tank is jacketed with cooling water inside of it. And we know that there is a flow of cooling water going in and a flow of cooling water going out. So in this problem, we want to find the change in concentration depending on the change in time, and we want to find the change in temperature depending on the change in time. So first we're going to start out by trying to find our concentration. So we know that the concentration of A inside of the tank would be the volume times the concentration of A. And volume is in the units of liters, and the concentration of A is in moles per liter. So we can see that our units would cancel out to just giving us the moles of A that are inside of the tank. So since we have an overflow reactor, our volume is constant, so we can put our volume out front. And we have dCA over dt. So then to find the change in concentration, we need to have the flow in times the concentration in minus the flow out times the concentration out. But since we know that our flow in is equal to our flow out, since we have an overflow reactor, we can just say that Q times CAI minus CA. So since we know that we have a first order reaction, our reaction rate is going to be negative RA is equal to K times the concentration of A. So we need to subtract this from our balance equation. But we know that this is just the volume, this is volume based, so we need to multiply that by the volume. So we need to subtract volume times KCA. So now if we try to isolate dCA on our left-hand side, we get dCA over dt is equal to Q divided by V times the concentration of AI minus the concentration of A minus KCA, since those volumes cancel. So here's our equation for the change in concentration over the change in time. And now we are going to try to find the change in temperature over the change of time. So we're going to do this as an energy balance. So we're going to start off with our temperature, which we know is in degrees Kelvin. And to change the temperature into energy, we know that we can multiply by the heat capacity, and that is in units of joules per gram Kelvin. And we also know that we need to factor in the volume of the tank. So we're going to multiply this by the volume, and that is in liters. And we can see that we want joules as our final unit, and right now it's not canceling out, so we also need to multiply this by the density, which is in grams per liter. So we see that we would get joules from this, So we can have this be the left-hand side of our equation. But we know that our density, our volume, and our heat capacity stay constant, so those can go out front. So we can have the density times the volume times the heat capacity, dt over dt. And then we're going to do the same thing we did for concentration. So we need to have our flow going in times the change in our temperature. But we also need to have that multiplied by our density and our heat capacity, since we need our units to cancel out. So we're going to have the density times the heat capacity times the flow rate times Tn minus T. So now we also know that our overall heat coefficient, so that's U times the area times T minus Tc. So that factors in our cooling water temperature. So we need to subtract this from this equation. So we're going to have UA times T minus Tc. But then our book in this problem also gives us the negative delta H of the reaction. So we need to add that to our equation. So we're going to have the negative delta HR. So that's the heat of our reaction. So we need to multiply this by our rate of reaction times our volume. So we're going to have VKCA. And now we are again going to isolate our dt variable. So we're going to have that the change in temperature over the change in time is equal to the heat capacity and the density will cancel, so we'll have Q divided by the volume times Tn minus T minus our UA divided by our rho V heat capacity times T minus our cooling water temperature. And then we are going to add our volume cancels. So we're going to have our negative delta HR times KCA divided by rho times the heat capacity. So now we have both of our differential equations for this problem, but we can see that both our dCA over dt and our dt over dt have two dependent variables right now, so we need to solve for k. So we're going to use Arrhenius' equation, so it's k is equal to k naught times e to the power of negative e over RT. So our negative E is the activation energy of this system, and since we are told that is exothermic, our activation energy graph would look something like this. So it shows that the activation energy of our reactants is higher than the activation energy of our products. So now we are ready to go to Colab to code this problem. Okay, so to start our code, we are going to import numpy, plotly, and our solve IVP. And then we are going to initialize all of the values that were given to us in our problem statement. So I have my book here that gives us all of the initial values down here. So we're going to enter all of those. So we have Q is equal to 100 liters per minute. We have our CAI is equal to 1 mole per liter. Our TI is equal to 350 degrees Kelvin. Our volume is equal to 100 liters. Our rho is equal to 1,000 grams per liter. Our heat capacity is equal to 0.239 joules per gram Kelvin. our negative delta HR is equal to 5 times 10 to the 4th. My numlock got turned off. 5 times 10 to the 4th joules per mole. Our E divided by R is 8,750 degrees Kelvin. Our K naught is equal to 7.2 times 10 to the 10. And this is minutes to the negative first. Our UA is equal to 5 times 10 to the 4th. And that's joules per minute Kelvin. And then our CA naught is equal to 0.5 moles per liter. And our T naught is equal to 350 degrees Kelvin. So now if we look on the next page of our book, we see two graphs. And our code is actually going to replicate these graphs. So our book wants us to try out 290 degrees Kelvin and 305 degrees Kelvin for our TC, which is the temperature of our cooling water. So we're going to initialize TC as 290 for right now. And that's degrees Kelvin. And then we also see that our book's graphs do the time for this reaction as 10 minutes. So now we are ready to define the right-hand side of our equation. So we're going to do define right-hand side, and we're going to go from our independent variable, which is time, to a vector of our dependent variables. So now we're going to unpack our vector, and we need to have our concentration and our temperature. So now we're going to initialize our value for K, since we use it in our T equation and our delta, our change in temperature over our change in time equation that we found on the whiteboard. So our K is equal to K naught times the exponent, or the exponential of negative ER. So our book had already found the value for E divided by R for us. So we're going to do that divided by RT. And now we are ready to put in our dCA and our dt. So we can do dCA dt is equal to our Q times our CAI minus our CA, all of this divided by our volume, and then we're also going to subtract our K times our CA. Now let's enter our differential equation for temperature, dt, and this is Q times Ti minus T, all of this divided by the volume. And then we are going to subtract our UA divided by our rho times our volume times our heat capacity. Also multiply this by our temperature minus our cooling water temperature. Then we're going to add our negative delta HR multiplied by K times CA divided by rho times our heat capacity. So now we are ready to return these values inside of an array, and we need to use an array since we are trying to find two different values. So we are going to export our dCA dt and our dt. So now we can use solve IVP to evaluate these differential equations. So solve IVP. we're going to evaluate our right-hand side from 0 to our time. We also need to initialize our dependent variables. So we need to have an array of our CA naught and our T naught. We are going to use the method redo. And then we need to have our dense output equal to true, so we can evaluate this equation at any time that we would like. So our code did work, so now we can use the common ODE solution object to actually solve this. So we're going to set this equal to result. And then we are ready to plot these. So I am going to copy over our t-plot, and we are going to do this from, where's my cursor? 0 to our time, and let's say that we want 500 points. Oh, forgot to change this to result. So now we can see that we have two different arrays here. Oh, where's our other array? There we go. So this array is our concentration, and then this one down here is our temperature. So you can see that it does work. So now we want to have a plot for our concentration and for our temperature. So we're going to have CA plot and our T plot. And then we are going to copy over our make subplots. So since we want two different plots here, we're going to say that our rows is equal to 1 and our columns is equal to 2. Now we are going to plot our CA first. So we're going to have our y is equal to CA plot, our row is equal to 1, our column is equal to 1, and we are going to name this CA. And then we are going to do the same thing for our temperature. We are going to have this be our t-plot. Our row is still 1, our column is 2, and we are going to call this our temperature. And let's just say that we want a width of 500 maybe. We'll do 1,000. And then we're going to do our height as 500. Alrighty. So we can see that in our book and on our graphs, our temperature starts out at about 350 degrees Celsius or degrees Kelvin, and it drops down to about 315. And then for our concentration, it starts out at 0.5 and it raises to about 0.95. So our book and our code are saying the same thing. So now we are going to run this at the other temperature that our book is describing, which is 305 degrees Kelvin. And we can see that there are oscillations here, and our book is also showing oscillations, so that does mean that our code is running correctly for this reaction. So our code and our book for the concentration start at about 0.5, and they go all the way down to 0, and then oscillate between 0.3 and about 0.03. And then for our temperature, they both start at about 350 degrees Kelvin. They go up to around 440 or 440, and then they oscillate between about 410 to about 360. So our code was successful for showing these temperature dependent and concentration dependent graphs. So thank you for watching. Hope you enjoyed.